This conference will now be recorded.
Okay, so JP, last chance.
JP had some audio issues, I think. He just pinged me. He asked me if he was able to hear me. I told him no, and then I think he's working on it.
Okay, so why don't I get rolling with the 4 slides I had, and then we'll go for the next. We'll go for the next, the actual show and tell, and then I'll hand it over. Sham, you still have your. I'm assuming you have your slides on your laptop, right?
Yes, I do.
Yeah. Okay, so we're good to go. So here's what, at least I'm excited about. Um, so starting about 4 weeks ago, we suddenly had a shot at doing a solid demo for the literally as late as 4 to 5 weeks ago. We had a shot at doing a solid demo for the global summit that just got postponed. And in fact, we got a point to where the team was able to assemble a demo at, I'd say, about 3 weeks' notice, thanks to sort of a really good catalyst work from Sham at Lattice and then from Kevin at Facebook, who's online. And then Vijay and team really managed to get a board design going at a time when the West Coast was capacity constrained. So in today's, what I'd like to do today is just walk you through. This is the poster I prepared for the demo. So essentially what we have, we call it the workflow POC. This is what we're demoing today. And the workflow POC is a prototyping platform for a chips to chiplets workflow. And the idea is that once we can also serve as a software development platform, it'll probably be the equivalent of a bring up platform for the package POC when it's ready. But the idea is that we can take the components in the workflow POC and put them together into a packaged part. And the thing about the workflow POC is it's a flexible modular platform with a baseboard and daughter card structure. And the daughter cards you can mix and match different kinds of daughter cards for various kinds of configurations. Our initial vision was that the three components would be a NIC, a CPU, and an accelerator. And the idea is that we could take these things we could take a package part that existed today, put it on a daughter card, insert it on the insert it onto the baseboard, the Mara baseboard, and develop software for that particular unique configuration. What we're trying to do as a group is make all of this reusable, and that's where the basic design is elegant in that today we have a NIC, a CPU from NXP, a package part, a security and management part from Lattice. We're working our way towards getting an FPGA into the design. But tomorrow, if somebody had a particular fixed function, much more targeted accelerator like a video transcoder or an inference engine, they could pretty much reuse the NIC and the CPU and just replace the FPGA part. Or somebody, if there's a of an alternate CPU, that could be replaced. So our longer term vision is that as we move forward, the workflow POC would add the stack being developed, the die-to-die interface being developed by the rest of the ODSA, take the components, take the chips in there, produce new die with new products with a die optimized interface, and do a second package POC. So this is roughly, we're here, and we would like this to be a good precursor for a chips to chiplets workflow, and later lay the foundation for a die to die optimized chiplets workflow. Right.
When do you think, Bhapi, the latest one you're showing, what's the time frame for that? The BOW specifically.
Well, the BOW, let me see if Mark Kemmerly's online. And no, okay. So I can, so the BOW right now is at a 0.8 spec, I think, or we were targeting a 0.8 to 0.85. What we're hoping for is that by Q4 of this year, we have a complete spec that somebody can use as a foundation for implementing it. And then, you're looking at a standard silicon timeline in my mind of chips with the bow interface being available next year. So our idea is that 2020 we optimize the chips to chiplets workflow, and 2021 is when we have chiplet or with optimized die-to-die interfaces.
That is a BOW stuff. That's 2021, you're saying?
Yeah. I mean, assuming we get the spec stabilized by the end of Q3.
Okay. I would be maybe offline interested if we can expedite, like what does it take to do that earlier?
Fantastic. Okay. Yeah. So the Bow group. I'll add you to the Bow group. This is a discussion worth having this Wednesday. There are two companies which are sort of actively looking at implementation. So there definitely be a lot of interest in expediting that sequence.
And which are the two companies, if I may ask?
They're kind of, well, I would love to share, but I've been beaten on the head twice saying don't share. So
I thought it's called Open Compute.
yeah. But I'm sure they'll get in touch as soon as they're interested.
Okay. Look forward to Wednesday then. Thanks.
Any other questions? Okay. So the advantage, the biggest thing that we're seeing with the chiplet prototyping platform is that we want to have a mechanism to leverage existing technology. We want the ability for us to sort of mix and match parts fairly easily, and most importantly, we want to make it get software development going, so that when there's package parts, we can actually port the software we're developing to the package parts fairly efficiently. Anybody else involved in the POC, if you would like to add your thoughts, please do so. I'd be more than happy. So Kevin or Jawad or anyone else?
I will be talking about some of the challenges that would come as far as security and control and management comes into play. I'll address that during my presentation.
Right, of course. And so what you're going to see now is there's a baseboard with the code name for the baseboard is Mara, and the baseboard has 3 daughter cards. And one of the decisions we just made is that about 6 weeks ago is that we wanted to build a adapter card to reuse OCP NIC 3.0 cards. And the exciting news is there's a good family of OCP NIC 3.0 NICs that we could reuse as is. And Xilinx just announced an OCP NIC 3.0 daughter card that we think we'd like to reuse as is if we can. And then Lattice is an actual pitchlet. So the daughter cards, we call them PCB pitchlets. Lattice has an actual pitchlet, and NXP has a pitchlet well in the design phase. Those are the 3 parts we have now. I'd like to hand it over to Vijay. If anybody has any questions, happy to answer them. Otherwise, I'll hand it over to Vijay.
Hi, Bobby. This is JP. Sorry,
Hey,
I
JP.
had some network issues. You couldn't hear me. So, Bobby, I'd like to give you an overview before we hand over to Vijay. Is that okay?
Sure. Here, the screen's all yours. Let me make you the presenter.
Yeah, thank you. Okay, I think I have the screen now. So, good morning, everyone. And my name is Jayaprakash JP. I'd like to give you a quick overview of what we do in the POC. A little more detail is what Bobby was talking about. So before we see the actual demo, the main purpose of this meeting today is to give a live video demo of the boards we developed so far and how we what we have in the pitchlet prototyping platform. Right. So do you see my screen?
Yep.
Okay. Sorry. So let's start with a quick overview of the platform itself. Right. The platform is mainly for enabling chiplet validation, architecture evaluation, testing, and software development. Right. So the problem today is we have chiplets from multiple people or multiple suppliers. We don't have a way to connect them together in a simpler fashion. Either you have to develop your own package or you have to have your own design a new board altogether. So what we are doing at ODSA is kind of standardizing the interfaces. So if you have chiplets from different suppliers, they can be glued together on the same platform with minimal efforts. Right? As long as we follow the standard that we have, it'll be a lot easier to glue them together at a much lower cost and much less time. So the main purpose being that when your initial phase of a chiplet development, you want to evaluate the architecture and you want to develop software. More importantly, also you want to test that whether the chiplet flow works for your design. Right. So the other thing is actually what the platform consists of. The platform consists of a base board. You can think of this as the motherboard and 3 slots, what we call a pitchlet slots. And pitchlets are a daughter card where the chiplet is going to reside, right, on the PCB. And it's designed to support variety of use cases in networking, storage, and AI, different type of acceleration applications. And it will support a host interface to the server via PCIe. You'll have a network interfaces such as QSFP, SFP interfaces via Ethernet. And it'll also have storage interfaces through M.2 NVMe. So the interconnectivity between the pitchlets or chiplets will be a full mesh high-speed wiring topology, and will support variety of clocking schemes. For instance, you have embedded clock, common clock, or source synchronous clock. It can be used to connect in variety of clocking modes, and also support single-ender and differential signaling as well. So all in all, it will be a very flexible platform with protocol agnostic wiring interfaces that can support data rates from anywhere from 1 megabits per second to 112 gigabits per second. The connector and the interconnect design we have been doing on the base board will support very high data rates up to 112 gigabits. Okay, and so we have today for demo, we have 3 pitchlets. So one is what the Bobby has discussed so far. One is actually a Broadcom NIC 8.6 via interposer pitchlet. So we'll be able to take a Broadcom 3.0 NIC as this. I'll be able to use it as a pitchlet or for chiplet validation. And we also have a lattice FPGA pitchlet for management applications. And Sean will go through in more detail, but the high level, what we're thinking is we'll have a RISC-V CPU, secure boot, voltage sequencing, configuration and status monitoring application. And we'll also have an NXP multi-core ARM processor, plus we'll also include some dedicated accelerators for storage and compression applications. And so this is the platform that what Bobby was talking about. I want to give a little more detail. This is like kind of SmartNIC type of acceleration platform for compute and storage acceleration. So you have a Broadcom NIC 8.6 that will connect to the host, and it'll talk to the NXP accelerator. The NXP accelerator will turn some acceleration inside the multi-core ARM CPUs, as well as it can offload storage to this M.2 FPGA for storage as well as for any other machine learning applications. And the lattice FPGA will orchestrate both the management of Broadcom 3.1x as well as this NXP accelerator. Right, so this is the overall demo setup we have today. And we also plan to have more pitchlets in the same platform, for instance, FPGA and other AI-specific accelerators. Okay, so that's the kind of overview I want to give. And any questions before I hand it off to Vijay?
Maybe a quick one. You're saying anybody ran anything on it yet? Just like
Sorry?
Like, did you like
No,
what?
no,
I'm sorry.
Tawfiq, nothing yet.
Okay.
It's just coming together right now.
Okay. Do you have anybody lined up to run experiments on it? I'm curious.
We're
I'm sorry? You didn't come across. I couldn't hear you. I think you were saying, you said something.
yeah. The question is with JP whether there's any software anybody lined up to run software on this. We're beginning to we have a couple of use cases in mind. There is a separate software effort which is sort of just gathering steam. If that's something you can volunteer for. In fact, one of the things we're really interested in is taking stuff from some of the use cases from Catapult and seeing whether they can be ported to this board. That's been sort of very high on our interest list.
Okay.
Yeah, so this is what we call the stage 1 demo, and stage 2 we have more software and full functional features. Stage 1 this is actually truly a multi-company effort with different companies participating in it and contributing different parts. We want to make sure the flow comes out right, and we can do a design completely in open source across companies. And so in the stage 1, we kind of showcase that's something possible working across companies, different workflows, and we can still interface things together. So in the stage 1, we could actually power up these boards and mechanically they all fit together. There's a lot of mechanical design involved, intricate things. So those things actually are, all the issues have been sorted out, and we have a fully compatible design that can work, have a different pitchless slot defined by completely from different companies. So all these slots, daughter cards you're talking about, pitchlets are designed by different companies, and they all came together nicely and fitted. Right, that's the stage 1. The stage 2 will have software and more functional features.
Okay, thanks.
Yeah, actually, that's a pretty pretty important point for us is that this pretty much the design sort of originated in the open, happened in the open. We've got different companies designing these things, and just one big issue was whether the boards would fit together mechanically as they came together, because the standard was sort of being developed in parallel with the board itself.
Yeah. Okay. So there's no more further questions. I'll stop sharing and hand it over to Vijay. Okay. Stop showing. Okay, Vijay, do you want to take it over?
Yeah, hi. Good morning, everyone. My name is Vijay, and I work for Tamron, and we are developing the POC board that JP just explained, the OCP, and we call it the Mara board. So there's a baseboard and the pitchlets. I'm just going to switch over to my webcam. JP, are you able to see?
Oh, it is. I don't know how to make you. Hang
Yeah,
on.
we can see.
We can see the photo.
Okay,
It's
you're actually watching. I'm going to go over and start.
Is it a thumbnail for anyone else or just me?
I can enlarge it.
No, I think I can see it. Is this looks like it's a live video? So Vijay, are you sharing the live video feed?
Yes, it is a live video feed. I'm going to move over.
Okay. So yeah, great. We can see that. Yeah. So Bobby, do you see it?
I see it. For me, it's a thumbnail, and I'm trying to sort of figure out how to. I apologize for my incompetence. I'm trying to figure out how to make it like occupy my whole screen.
I just was able to expand the window.
Yeah, I just double click on the larger window and then it just expands to a full screen.
Yeah, the same way, the same as all the other windows. Just click on the enlarge. Right next to the cross on the upper right.
Yep. Okay. But Vijay, go. Oh, I need to make you the presenter. I'm sorry. Give me one
That's
second.
okay, Bobby. I think everybody's able to see it, so it should be good.
Yeah, but I'll make you the presenter, then yours will be recorded. And give me one second. I apologize.
Sure.
Make you the presenter. There you go.
Thank you. So we have the two boards here. One board is the base board, which is unpopulated, where you can actually see the actual board with three pitchlet options, the A, B, and C. And then you have the M.2s here, the power input. You'll have a 12-volt input, and then there'll be a 3.3 that'll be fed on the board itself. And then you have JTAG, reset buttons, and then you have the QSFP, 4-port QSFP coming in with USB serial, and you have your PCI Express connector that can be connected to your PC. And this is actually the board that we have developed. This is a limited functionality board right now. It's more for mechanical and basic power-up tests. And then in the future, we'll be having the full functionality board with the software that'll be running on it. And then right now we have three pitchlets. One is the NXP pitchlet that you see here, which is the processor pitchlet that we were talking about. And the lattice pitchlet, which is the management pitchlet, that is actually right now mounted on the second baseboard that we have developed, Mara board. And I have also actually mounted the interposer card, which is the NIC interposer card. And we have a Broadcom NIC actually inserted into the interposer. So I'm just going to show you. So as long as, yeah, there you go. This is the third interposer we have, which is the Broadcom card that's got inserted into the NIC interposer. And the NIC interposer actually sits on the baseboard. So if you have any NIC 3.0 cards, we'll be able to just use the interposer card and interface with the baseboard, and you don't have to actually develop any new hardware for it. And then you have the M.2s inserted into it. And right now with the demo, we do have a basic power-up test. Let us actually put together the fully functional card so we can actually power it up and you can actually see, and then we have actually downloaded a program into the FPGA, which actually runs the LED lights. And so the card is fully functional. I did have a lot more to talk. I think JP and Bobby pretty much explained all the other features on the card, and you can see the actual functional card working right now. This is what we were actually planning to, present it at OCP, which got moved. So we'll be doing it again in May. By then, we might have the fully functional features, but we're not sure. So in a couple of months, we'll have the fully functional card with software capabilities running on the system. Is there any other questions? Do you want to see anything else? Poppy?
Yep. Thank you. So our big deal here is to make this, to be able to take this and make a single package with the chips in this, with the chips in this in the demo, and to leave room for new packages in that you can mix and match chips from multiple vendors into this into the demo. Any questions? Okay, so our big part of the big, there are two reasons why I'm sharing this here. One is obviously the team sort of killed themselves to get this in place for the OCP Global Summit. The second is Taufik's question, which is around we'd like to get a software development effort all fired up on this and showcase the ability to add new functionality. So if you know of other companies with accelerators who could occupy a slot, I think it's reasonably safe to say we're open for business on this issue. Okay. Shyam, it's all yours. I'll make you the presenter. Vijay, thank you so much.
You're welcome,
Hey,
Bobby.
thanks, Vijay.
You're welcome, Shyam.
Yeah. So
Hang
the
on, Shyam.
board and the one that's showing its heartbeat in terms of LEDs is Lattice's secure control and management pitch set. Yeah, once I become a presenter, I'll be able to talk
Yeah,
briefly
I'm
about
sorry.
that.
I'm really incompetent at organizing the meeting today. I don't know what I'm doing wrong.
I think Vijay has to unshare first, I think.
Okay.
Yeah, but I've lost my menu for.
Let me see.
I have lost my menu to make you a presenter, and I'm wondering where
No,
it's.
I
Okay, you
am.
got it.
I'm sharing
Okay,
my screen. Just want to make sure
we
people
can
are
see
able
your
to.
screen.
Okay, so what I wanted to talk about is a system in a package, control, management, and security. So one of the so let me see what happened. Okay, so one of the things that people talk about whenever a system is developed, it's most of the time it's the data plane functions, and then there will also be now a lot more focus is given to the security of it, the control and management aspects. So now what we have done is we have provided a programmable platform that that can be made to control various types of systems. When you have different types of chiplets on the board, everything has different control functions. They're all focusing on the data plane that's standardized, but for the control and management, they're all unique. So a programmable solution would make it easy for putting the whole things together and provide a standardized output, control output to the final system in a package. So some of the adoption challenges that we are seeing in terms of control management and security focus is one is, of course, the non-standard SIP-specific control path integration. So, you will need different sequencing, different reset sequencing, power sequencing, telemetry. There'll be sometimes glue logic needed. These this is the on the chiplet, but when you look at the standardized SIP output, you would like to have a standardized control path, so that the SIP can be adopted in the system on the main board. One example is the management and control transport protocol, or MCTP, and there are different standards as specified in the OCP. And the other thing is when people say, okay, I want to build a system on a chip, if that SIP itself controlled its own power supply sequencing, then it makes it easy for the board designer to just plug in a new SIP and then use it across various types of systems without having to worry about implementing SIP specific functionality. So, and then also, if you are trying, sometimes people have to put the SIP into an existing system, and there it'll be incumbent infrastructure that is there, to which if they have to adopt, then we can bring in backward compatibility, and that accelerates the adoption. The other aspect is these SIPs are pretty complex. They are pretty much system on a chip. which means it's got its own firmware, it's got its own various programmable elements. And then if you need to be making it secure, you have to protect it in the supply chain. So this is where you need to be able to do key provisioning. You want to handle traceability. You should be able to attest, that is just to make sure that this has come from the original SIP manufacturer, all these aspects. And then also you want to have logs of all touch points. And so basically you would like to have a root of trust for reporting. So this can be, say this SIP can be a trustworthy platform. And also whenever you have a SIP, you would like to also ensure updates into the system, and you want to protect even the in-system updates that are possible. So this is yet another function that you need to consider. So these are some of the challenges that people face in this modern secure hardware platforms. So for that, what I've done is, any questions so far on the challenges? Okay, so what we have done is I'm showing the secure control and management chiplet in the center. It has source synchronous inputs. It has got power board power sequence and reset sequence functions. And then it can actually, it has ADC, so it can perform telemetry. It has a PCIe interface. It can implement I2C interface, or SMBus interface. And it has a on-chip RISC-V processor. It's a soft processor within the realized within the FPGA fabric. So it can interface with different types of chiplets while providing a standardized interface with the main system. So you can do things like power management, you can do power sequencing, you can do the, if you mounted the power sequencing, power sources on the chiplet itself, on the substrate itself, you could power sequence them and give a simple 12-volt input, and everything else is managed within, reset management, the security. This device is a root of trust module that uses on-chip cryptographic block to perform the security functions. It can also be used for attestation, that is to make sure that if you plug this chiplet in a system, they would like to know if the main platform root of trust might want to know if the chiplet has the authenticated one, if all the firmwares on it are authenticated, and so on. And the other aspect is NIST 800-193 specification. This is the latest. It was introduced in 2018. It's called platform firmware resiliency. So this device can perform the platform firmware resiliency of the firmware on the system, on the SIP. So there will be each one of these CPUs will have their own CPU, and network chip may have its own firmware, and this firmware can be combined into one chip or multiple SPI memories on the SIP. And this device can perform, detect, recover, and protect the firmware on the system. So this will be NIST compliant solution as well. And you can have a secure out-of-band communication where you can have use the MCTP protocol. This is the transport protocol, and then conform to those protocol standards. And this can also be a symbiont root of trust. That is, when you plug in the SIP on a system, you can be a part, it can be a slave root of trust to the main platform root of trust. So you need to have a very flexible environment when it comes to security. The other functions that we have is this can have source synchronous interfaces with other devices that can run at 1.5 gigahertz interface. So you can have a byte wide 1.5 gig source synchronous interface if you wanted to. One of the things, one of the applications is you can look at the processor utilization monitor. Suppose the processor had some, it ran some containers. You could take the usage of that, and then you can even run AI algorithms to monitor for malicious containers, for example, that gets launched. And you can have a PCIe interface for MCTP protocol. This is, some systems, they use SMBus for MCTP protocol implementation. Some systems use PCIe, so you can have PCIe there. And of course, we have other applications for the chip, something like a video camera interface. If you wanted to drive a video camera, it's got a DeFi interface as well, so you could use that. You can also use AI for predictive maintenance of the solid state storage that you have in system, or you can monitor the ADC, use the ADC for monitoring power supplies and look for something like tampering of this device. So there are many applications. Not all are relevant to one SIP, but you can select whichever one you want that is relevant to your system, and then a PLD device sitting here provides a fantastic, convenient way of implementing that. Any questions on the this particular chiplet?
Hi, this is Suresh. I have a question. On
Yes.
this source synchronous interface, how wide is that going to be? Or you said it's a 1.5 gig interface.
It can be 8 lanes.
Eight lanes. And
Yeah.
and the dominant use model here is in a packaged type of environment, or when you're talking about chiplet kind of system, this would be the BOW?
This would be a poor man's BOW, if you would call it. The BOW specification is a lot more sophisticated, so this could be used as a subset of BOW. So what this does is, and what this device is doing is providing a physical layer, and whatever you do on the physical layer, like how you're gonna go packetize things on top, you could use any which way you choose. This device gives you the programmable delays to make sure that we dial in we manage the data valid window on the physical layer. Did I answer your question?
Yeah, I got an idea. Yes, thank you.
Thanks. So one of the questions that when I spoke about PFR, platform firmware resiliency, sometimes people want to know what that means. So I've dedicated one more file to show what that platform firmware resiliency means. So here we have a secure control and management PLD. And this is a processor, FPGA, and or an SoC booting from a SPI flash. We add a SPI quick switch in series with this. So when you power on, what happens is the SEM is going to go hold this in reset and check if the SPI memory flash has authenticated software. This is what we call a detect phase. So the SCM is going to become a root of trust for detect. So it is going to go read the contents of the spy memory flash and see if it has using a public key stored inside the management PLD as a SCM device and validate this cryptographically. If it is good, then it'll allow the processor to boot from it. Otherwise, if it detects a particular firmware that is not good, it institutes a recovery, so it picks it up from a different location and then overrides the malicious or unauthorized firmware and replaces it with a good firmware. So the processor or the FPGA is always guaranteed to boot only from a trusted trusted firmware. And then afterwards, this device starts to monitor the transactions that go on the spy flash, and it looks at things like white instruction set. So the processor can only issue only fixed set of instructions to access the spy memory, and then it can only access the authorized regions. So there are three possible regions. One is called the white region, where the processor can read and write into it. Then it has got the gray region, where the processor can only read and execute the code that is there. And then the black region, where the processor can't even go access it, even if it wants. So that black region is available only for the SCM zone. So the spy bus will be dynamically monitored, and if there is a bad instruction that comes and accesses different parts of the spy memory, it'll be blocked, and there'll be a fault log, and then the main processor will be made known that such a event occurred. So it can go into the SMM mode and then process the fault. Okay. Any questions on providing the PFR implementation? PFR is actually designed. This is a NIST standard. This is designed to make systems resilient against attacks in the supply chain, and that's what this does. And if you have multiple firmware, all firmwares will be managed by the SCM.
So that's one area we're trying to figure out, and whether we can make a standardized management interface and security a simple package function, or is standardized in some fashion. You're using DMTF as a management interface, and the OCP NIC 3.0 management over the DMTF overlay as a standard management interface for ODSA as well. We're pretty clueless in that, but the general trend is, can we do something there?
Yeah. So
standardized management across chiplets.
Right. That's what I was talking about, the MCTP. This is something that we believe is going to be very important in adoption of a chiplet. Adoption of a SIP. So this provides overall solution, overarching management interface. It can take the inputs from different modes from each one of this. So suppose the CPU had its own management interface, this could just be a pass-through for it, for example. And if there was a device that didn't support, this can provide the support for it. So this provides a flexible a platform for integrating multiple management functions and provide one consolidated interface. Like for example, it can do the MCTP over PCIe, vendor dependent module. So you could do that too. So multiple ways, and it depends totally on a particular platform. If a platform cannot accept PCIe, we can do that on I2C. So we can switch physical layers and yet support the same level of protocol. And the protocol is open, and we can just adopt the standard protocol.
Hey, so I just want to spend 2 to 3 minutes on the potential data flows we're seeing. So if Taufeeq can take it back to his organization, Sham, if you don't mind, I want to burn about
Yeah.
5 minutes on the potential
Yeah.
use cases that we're looking at.
Okay. Let me unshare it.
Thank you. So I want to share. Taufeeq, you're still with us, right? Yes.
I'm with
So
you.
yeah, so basically the big thing about the OCP 3.0 NIC is it's a multi-host NIC. And especially, once we get to PCI 4.0, I think we'll have the bandwidth needed to look at some of the data flows. So there's a whole bunch of offload and stuff, but I want to burn a couple of minutes. So what we're thinking is that we're thinking three things. One is, if we have like a basic reference design, and this is where I think there's room to work with ASE and a few other packaging vendors and packaging experts. In sort of, can you make security a part of the base design in some fashion? More importantly, the applications or equally importantly, the applications we're looking at, we want the NIC to be some kind of a traffic splitter where if you can, once you can split traffic in a multi-host structure, there are 2 or 3 use cases we're looking at. One is the classic case of offloading the fast path. So all the traffic, if it can be processed by the fast path, it doesn't get sent to the host, but gets offloaded onto the card itself. The second is the energy department has a very interesting use case for something they call a data transfer node. They've got their own version of Akamai effectively to transfer large data sets from their research experiments between various energy department labs and equivalent labs in the rest of the world. And the basic design is something called a data transfer node, which is sort of a very similar to an FTP transfer node. And the idea there is data comes in and essentially stays on the package part, gets U-turned right away without ever actually touching the x86 host. And finally, one more application we're beginning to look at is some kind of flow mirroring and using flow mirroring to manage and monitor data going to the host. So you can sort of say data goes to the host, but we copy selected flows over and process them on the inside the package or on the card if we're using the piece if we're using the development platform. So this is sort of the nature of the apps we're looking at. So the accelerator could be compression, inferencing, transcoding, or a plain or an FPGA where you load an arbitrary function. That's basically what we're thinking of right now. Does that make sense?
Yeah.
Okay. Any questions? I'm happy we got the opportunity. It would have been great to show it at the OCP summit. I think the team has pulled off a minor miracle in the way they've assembled this board and with different vendors and participants. So our next goal is to integrate an FPGA. We're definitely looking for software help. And if you have people with accelerators, they should be able to reuse a lot of the infrastructure we have in place. They can reuse the CPU infrastructure, they can reuse the NIC, and just drop their accelerator in. And that's my primary motivation for sharing. Our primary motivation for sharing this effort. I want to thank Shyam's company, Vijay, Jawad, Kevin, JP, for really gluing this all together. This is when we'd give them a big round of applause if we were all in one room, but
We can do it even if we're not more than one room. Very
Thank you, Ravi.
Thanks, Bobby.
Any other questions? Any thoughts?
Nothing
If not,
here.
thank you all. Everybody enjoy your weekend. Thanks for listening in.
Have a good day,
Same
guys.
hope, y'all.
Have a good day.
Thank you,
Bye-bye now.
everyone. Take care. Bye-bye.
Bye.
Bye-bye.
Yeah, bye.